So, of course, you remember that there is a test on Tuesday, but that Tuesday we do have class. Okay, the test is at night. It will be open for 3 hours from 8 to 11. So make sure you are available. It's online. It's going to be some numerical questions, but a lot of conceptual questions, you know. So make sure you have your right hand and with you. You can print out, you know, the last page of the slides. So the two set of slides, 3.1 and 3.2, at the very end, you have the equations and the explanation. So make sure you go over the equations and what else? I forgot. So there won't be any induction, what we are doing now. So it's not on test 3, it will be on the final. So don't forget. And we do have class on Tuesday. It's not spring break anymore, okay? So we do have class on Tuesday. And today there is no pop quiz because I want to show you video. So no pop quiz today. So we take a break from pop quiz. So I would like to go over and introduce a physical quantity that I didn't last time. So first of all, when you have an electromagnet or a permanent magnet, so here you have permanent magnet, you see here, you see field lines. Like we had also for the electric field, we had electric field lines, okay? And you can show with those lines in which direction the magnetic field is flowing. And you can see the magnetic field always likes to curve from the north through the south back to the north. Okay? Any point here, you can trace a magnetic field vector B. So at that point here, the magnetic field will be in this direction. My point is that if you have a stronger magnet, you're going to show that with a more magnetic field lines. Okay, you're going to have a larger density of lines. Is that clear? Okay, so that's a way. Those lines are a way to show you how strong is the magnetic field and also which way it's flowing. So those are magnetic field lines. Okay, and so we can define, so you see those magnetic field lines. So you see here you have a loop. Okay, so it's a conductor, nothing is happening. It's a closed circuit, but nothing is happening. Now you can imagine that you have an imaginary area. So that area will be like let's see, I have a picture. Soap. Of course, I cannot find a picture I wanted to show you. And I don't have my slides. Where are we? Okay, you see here? Do you see here that film here is like a soap film? So that could be thought like an area. Okay, imaginary area. So let's go back to here. Imagine you attach an area. Can you see, and do you agree with me, that those lines are poking through this area? Can you see that? Okay, so let me define a new physical quantity. We're going to introduce a quantity that we're going to call the magnetic flux. Okay, the magnetic flux, the notation will be phi, so it's an uppercase phi. So it's a Greek letter. Magnetic flux, you can think of that as the number, okay, of field lines poking through an area. So for example, let's say you have a coil, okay, so it's a loop here, and you have wire going around and around and around, okay? So maybe here it's attached to a load. For example, if you want, you can have a load here and there is no current flowing. So it's just a conductor and it's a loop. So you can imagine that you're going to attach here an imaginary area. So imaginary area, you can think of that as like a saw, a film, you know, like here. So you are attaching an imaginary area. And now let's say you have a magnetic field. And for this class, we always have the case when the magnetic field here is perpendicular to this area. So this area, so it's an imaginary area. Okay, you can think like rubber that you can attach to this loop. So it's a coil here. And you see this magnetic field here. Magnetic field is, so you have the lines, the magnetic field lines. So can you see it's poking through this area? Okay, so maybe here you're going to have a north, okay, and maybe here you're going to have a south. Maybe you have a, remember the Helmholtz coil, so you have two electromagnets here, okay. I already show you the Helmholtz coil. Okay, you have to go back to the big idea here and go back. Here, you see, if you have two coils and they are perpendicular to each other and the radius equals to the distance between them, so you're going to have a uniform magnetic field. Okay, so anyway, let's go back to here. So maybe there is a coil here that will be the face, that face is the north, and that will be the south, that will be the north. So you have magnetic field lines. Now you have a conductor, so you have a loop here, and you see those lines are going through, poking through this imaginary area A. So that will be the area here of the loop of current. It doesn't have to be a circle, it could be a square, for example, or a rectangle. So can you see those lines are poking through magnetic field lines? Yes? Okay, so what is that new physical quantity? We call that the magnetic flux. That's going to be a way, and it's an easy way to think about it. That will be a way to find how many lines, how many magnetic field lines are poking through this area. Okay? So in that case, you see the magnetic field here is B. And in that case, it's perpendicular to this area. So that will be for the computation always the case. Otherwise, you have to introduce a cosine somewhere. But in that case, the number of magnetic field lines will depend on what? First of all, it will depend on the it's like you have water flowing, you are in marine biology, and imagine here you have little shrimps, you know, they don't swim, they are just carried by the current. So if you want to increase the number of shrimps, you need to increase the area. Very good. So the number of feed lines poking through, it's going to depend on the area. And of course, it's going to depend on B. Because if you have a strong B, so let's say you have a very strong magnet, you're going to have a lot of field lines here, like that. If you have a small magnet, not very strong, very weak, the number of field lines will decrease. Okay, because we are using field lines for two things: showing the magnitude of the magnetic field lines and also showing which way it's flowing. Is that clear? So you can change B. And because you have, in that case, you have n loops, okay? So it's gonna add up. So you're gonna put an n here. So that will be called the magnetic flux. So you can think of that as being the number of field lines poking through this imaginary area, okay, attached to your coil, okay? Is that clear? I should be adding here a little sign because that will be only for perpendicular. It has to be perpendicular. Okay, otherwise I will have to introduce a cosine somewhere. So this is called the magnetic flux. Magnetic flux. The unit here, the units is Tesla. Okay, this is in Tesla. This one has no units, it's just the number of turns. Okay, so that will be the number of turns. And area is meter square. And we take a shortcut, and this will be called also the Weber. Okay, WB. Okay, it's the unit for flux. So they will be equivalent to each other. So again, what's the magnetic flux? It's the number of lines poking through an area here. So this area that you attach to your coil. So this is a coil. Is that clear? So likewise, to go back to my app here, you see, those field lines are poking through this area here. Okay? So here it's not maybe a not very good example because I want to suppose that the field lines are perpendicular to the area. But you see, you have field lines poking through this area. Do you agree? Okay. So what's going to happen when I move back like this? What's happening to the number of lines? Are they the same or you have less line poking through? Less line. Do you agree? Here I have only two. And if I go in, what's happening to the lines? Increase. So the secret behind producing electricity using magnetism is to change the number of field lines poking through the area here that you attach to the conductor. So if you increase the number of lines, decrease, decrease, and you can do that in different ways, right? So here I'm moving the magnet. You can move the coil also. You can turn the coil. All that will do it. Is that clear? So you see that if I do that, what kind of voltage do I get? Do I get a direct current or do I get a alternating current? AC. Okay, that's the only way we can produce electricity and be able to transport electricity from very far away where the power plant is to us. Okay, you can only produce AC. And you see, if you change the number of loops, you're going to get less voltage, more loops, more voltage, because it keeps adding up. So the genius of Faraday was to understand this. He understood that if you want to induce an EMF, that means if you want to induce a voltage, that is, if you want to induce a current, you need to change the number of lines poking through this area. That takes us to this very famous equation, which is Faraday's law of induction. The EMF, so the voltage induced will be equals to the number of loops times the change in the number of lines poking through. So there will be a delta here. over time. So it's a rate change. To be able to induce electricity, you need to change the number of lines poking through. And that will be the definition of the EMF. Again, how do we define phi? So phi, you know what? I'm going to remove the number of loops here because it's there. Okay, so I'm going to say that the magnetic flux is the area times the magnetic field. So it will be area times the magnetic field. And I suppose the magnetic field is perpendicular to the area. So the EMF will be equals to the number of loops. You can put n here, but don't put twice. Okay, so I took the n out. It will be the number of loop. That's going to be A2B2 minus A1B1 divided by the time elapsed. Okay, so that's what we did last time. Where are we now? Okay, so here again, you can print out this page. It comes from your book, and you see the flux will be equals to the magnetic field times the area, the magnetic field lines are poking through. Okay, that cosine means that we are only taking into account the magnetic field lines perpendicular to the area. And that will be the definition for the EMF, the number of loops times the rate of change of the flux. Okay, so the number of lines poking through the area has to change. So that's Faraday's law of induction. Are you with me? So you see here, you take a coil. Okay, it's a conductor. You can attach that to a load. And you see that as you move away, you're going to have less lines poking through. As you move toward, you're going to have more lines poking through. So you're going to induce a current. You can change the area, okay? So for example, here you have a large area. So you're going to have a lot of field lines poking through. If you decrease the area, what's going to happen to the number of lines poking through? It's going to be less. Does it make sense? Okay, you reduce the area like this. You see, you have a conductor. The magnetic field is going where here? In the screen or towards you? You see the cross here? So the magnetic field is going in the screen or towards you? When you see a cross, it's in the screen, right? Don't confuse that for test number 3. Huh? If you see crosses, it means in the screen. It means I don't like you, I put a cross on you, so I'm canceling you out. So it means away, in the screen. And so here you see you are stretching out the loop. Okay, so you're going to have less field lines poking through. Okay, if you increase the area, you have more field lines. Same thing, we're going to do a problem with this type of situation. Is that clear? So I made a video for you. I combined several videos to make sure it's you understand. So in those types, like if you have like for the MCAT or conceptual questions, the math is not heavy. It's the concept. Okay, so conceptually, it's not that easy to understand.
The field of a bar magnet.
So here, okay, you can see that's a bar magnet. So you can see the field lines. If it's a weaker magnet, you're gonna see less field line. Is that clear? Okay.
Can be perpendicular at every point to a circular loop of wire.
Okay, so you can take your loop, your coil. It's a conductor. the number of lines poking through, that's going to be called the flux, okay, the magnetic flux. Nothing happens here. Something has to move.
So, moving the loop creates a way if the loop moves
So you see,
upward,
when you move the loop, what's happening when you go
and the other
down?
way if the loop moves
You
downward.
increase the number of lines or you decrease? Increase, okay? You have more lines poking through, right? And if you
Of course,
move it
a
up,
current also
it's going to
flows if the
decrease the
loop
number
stands
of
still
lines.
and the magnet moves.
So, for example, you decrease
One
the
way
number
if
of
the magnet
lines
moves downward.
poking through this area. It's an imaginary area that you attach to the
The
loop.
other
And
if the
here
magnet moves
you
upward.
increase the number of loops. When that happens, you're going to induce
In
the
fact,
current.
Faraday found
So
that any
imagine
method of
the
changing the
beauty of
magnetic
that.
field through a
You are
circuit
getting
would make a current
electricity
flow.
almost for free. You need to have some, like what he's doing here, you need to have some motion. Okay, you just move a magnet inside a closed conductor and you have electricity. It's very cheap to produce. Okay, so you are turning mechanical energy into electrical energy via a magnetic field. You can see here again, you have magnetic field lines. The magnetic field is uniform because you see the lines are equally spaced. So you can get that with a two coil, for example, inside the MRI. So you go inside the MRI, you have coils, and it will produce a uniform magnetic field. So it's going to be constant all over. And what you can do, you can
Current flows through a coil of wire whenever the magnetic flux through it is changing.
decrease the strength of the magnetic field.
The current
you
flows
have
one way
less
if the flux
lines
decreases,
poking through. By doing so, you are
and the other way
reducing
when the
a
flux
current.
increases.
You can increase the magnetic field, so you're going to have more lines poking through, and you also induce a current, but in the opposite direction. Do you understand?
But the current induced
Okay.
in the wire
So
also creates
the
a flux of its own,
is the number of
whose
lines
direction
poking through, and you need like this also works, right? Look at this one. Are you watching? I see people like spacing out. Don't space out. You see here, you're gonna turn on and off an electromagnet. So the field lines will increase and then decrease. As long as it's happening, you're gonna induce current. You see, you stop, you increase, you decrease, you increase, you decrease, and you are inducing a voltage. So that's how we generate electricity in the real world. So you have a magnetic field that you can produce with an electromagnet, and you have a conductor that you make it spin at a constant rate. So so what you're gonna have, it's gonna rotate 60 times per second. So you're gonna get a frequency of 60 hertz. That's gonna be the frequency that you get here from the outlet. That's how we produce electricity today. You have a magnetic field here, okay? You're gonna rotate that conductor there. So the number of field lines poking through is going to change with time.
rotating a loop of wire in
So
a
for example,
constant
here,
magnetic field,
maximum, what
continually
about here? Look at that. Do you have any field lines poking through? Do you see lines poking through this area, this green area? No, zero. The flux is zero. And then look, the flux, like imagine like shrimps. Shrimps inside the flow of water. You're not going to catch any shrimp. Agree? Okay, can you pay attention? It's all conceptual questions. You know how I love conceptual questions. So don't space
changes
out.
the flux
Look
through
at
the
that.
loop.
It's going to increase. Ooh, do you have lines poking through? Yes, maximum. So what matters to induce an EMF is to have the number of lines poking through increasing with time. and here they increase at a constant
The
rate.
resulting voltage and
So this is
current
how
are
we produce
sinusoidal,
electricity
going first
that
one
you
way,
get here.
then the other.
You see, you have an AC, okay, voltage.
The field of a bar.
So, for example, if no, here we already show you that. So that's called a generator. Let's look at the field lines here. So can you see the field lines coming out of the north, out of the north? You see those little compass, they show you which way the magnetic field is flowing. And if you connect all of them, you can see the lines. See these lines going out of the north, blah, 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 into the south, back to the north. Now, you see, you have lines poking through. So I could find the flux, okay? So the number of lines poking through this area. All I have to do is to find the magnetic field and multiply by the area. But nothing is happening there, okay? So something now you have induced current because the number of magnetic field lines poking through is changing with time. So let me assist something like typical for a pop quiz. If you have, oh, that's a good one for a pop quiz. So you see the magnet is this way. So the magnetic field is parallel to the magnet. Do you agree? When you have a bar magnet, the magnetic field will be parallel. Do you see any lines poking through? No, very good. Okay, it's like water flowing in this direction. No water is poking through. And then here, it's going to be maximum and maximum again, except it's flowing the opposite direction. So that's how we produce AC. Okay, you need what it's called the rotor. So something has to spin. Okay, it's called a turbine. How do we make it spin? You can use water if you have a hydraulic power plant, or you can burn fuel, you can burn fossil fuel, you can burn nukes, for example. Okay, so the turbine will spin, and that's how we produce electricity. That will be a load. You see how it works? If I increase the area, okay, I'm going to increase also electricity. I'm going to increase the EMF. So the EMF does depend on the area. And if I make it faster, of course, I have more, I'm getting more voltage, but I get AC. Okay? So conceptually, it's not that easy. So I want to go back to something else because that's going to be on test number 3. So I'm hoping that you understand. Because I didn't think that I want to go back to this motor. So that was the first motor ever built, and that was done by Michael Faraday. And he used mercury. And someone said, you know, you can use salt water. Was it you? Yes. Today, if you want to make this one, you have to use salt water. You don't want to use mercury. But at the time, they didn't know that mercury was a poison. Okay, people didn't know, so they were handling mercury. And so that's why he used mercury here. What I want you to see is that the magnetic field here from the bar magnet, it's going to be from north to south. Okay, so it's parallel to the bar magnet. That rod, that it can spin. Okay, so it has imagine here, it has a little flat bottom here. So you take your right hand, the current is going in this direction. So that will be to your left. Do you agree? Magnetic field is up because it's a bar magnet, so the magnetic field will be parallel to the bar magnet. So the force acting to the bottom of this rod will be into the screen. Do you agree? So that's why it's going to rotate in this way. So this way will be into the screen back. So it will rotate that way. Do you agree? Because there will be a torque like this, right? It's going to spin in this direction. So it's going to rotate like that around the bar magnet. So this is called a homopolar motor, and that was the first one ever made. Okay, so last time I tried to show you one, but it was not working, so I fixed it. It's a student, okay? I'm not taking credit. So you see, very easy to build. You have a battery, and it works exactly the same way as the first motor built by Michael Faraday. So you have a magnet here. So the magnetic field is going to be parallel in this direction, because that will be the north, and underneath is going to be the south. And then I take something like this. So it's a copper wire. There is no insulation. And the magnetic force is going to apply the torque, and it's supposed to spin. Unless yes. You see? It has to be on the plus. And then it's going to start to spin. Isn't that cool? Very easy to do for extra credit. Okay? So this is called homopolar motor. So there is a different way to do it, which looks more like Faraday's. Oh, you can do it this way. So you see the magnetic field will be up and down. The current will be sideways. So the force has to be in the screen. Okay, so that's why you have a torque. Okay, so the easiest one to make, if you want to make that for extra credit, you need a battery, you need a screw here, and a magnet. The magnet is here, so that's called a neodymium magnet. You need a screw. The screw will get magnetized, so it will be glued to the battery, and you need a wire. Again, you're going to have the magnetic field in this direction. You're going to have the current in that direction. So you're going to get a torque. You're gonna see that here. Okay, so the current is flowing. That will be your magnetic field, the magnetic field here. And the current is flowing in this direction. So there will be a torque here and there. So you will have the twist happening and it's going to start spinning. Do you understand? So that's the idea. Okay, so someone on YouTube, I was looking for it. And oh, that's the one. Okay, that's the one you can do. You see, it's exactly the experiment done by Faraday. You see? But someone was able to do the experiment done by Faraday, but he used salt water. So that was the experiment by Faraday. That's what he did.
The wire is rotating clockwise around
in the
the
19th century. So
I'll
quite
disconnect the battery and
impressive
reverse
for someone who basically didn't go to college or stop school at 12 years old.
The motor
but
now
he was very
rotates
good at experiment. And you see here how it's spinning around the magnet. So he was a scientist, okay? He was not a businessman.
Bubbles and material
others
appearing around
took
both the rotating
over
wire
after that
and the
and
aluminum
improved
contact.
the motor.
We are witnessing
But he
some
got the
complex
idea.
electrochemistry.
Okay, so I want to make sure that now it's clear. Again, magnetic field is parallel to the magnet. That will be the current. So the current goes this way, magnetic field is up because it goes from north to south. So the force is in the screen. So it's going to apply a torque and make it twist. Okay, and the other thing I forgot to show you, so that's why we don't have pop quiz, because I wanted to show you so many things.
A magnetic field applies no force at all to an electric charge at rest.
So in blue, again, you have the magnetic field lines, and here you have a charge. Can you have a magnetic force if the charge is not moving? No force, right? It has to be moving, and it needs to move with a component perpendicular to the magnetic field, otherwise it doesn't work. If it's moving parallel or anti-parallel, there is no force. So here you have to make it move.
However, if the electric charge is in motion, there's a magnetic force called the Lorentz force.
Now there's a force which is called the Lorentz force.
It's perpendicular to both the field and to the direction of motion of the charge. The force is conveniently expressed using the vector cross product.
So that's calculus, so you don't have to worry about that. But you see, the force has to be perpendicular to both the magnetic field and the velocity. So that's why we use our right hand, because it makes X, Y, Z. It's like a coordinate system.
Because the magnetic force on a moving electric charge is always perpendicular to the velocity, the force doesn't speed it up.
So you see that force will change the direction, but cannot speed up or cannot slow down because you have no component of the charge along the velocity, right? Right? So this is called a centripetal force, right? So QVB equals mv squared over r. Okay, so
Or slow it down.
Circular.
Instead, charges tend to curve around the field in circular or helical paths.
So a charge wants to circle around the
In non-uniform magnetic fields, electric charges can be trapped, as they are, for example, in the Van Allen radiation belts. Near the polar regions, charged particles sometimes get close enough to strike the atmosphere, giving off light like electrons striking a television screen.
So that's how we are protected. Okay, are you paying attention? You know how much I like conceptual questions, so don't space out. If you want to socialize or talk, wait. So how do we produce the induced current? Okay, so you need to have a closed circuit like that. You can move a magnet in and out. So if you don't move it, nothing happens. You have to move it. Okay. Or instead of moving the magnet, you can also move the coil in and out. The idea is to change the number of field lines poking through this area. Or you can use two coils here, and this one will behave like a electromagnet because you have a power supply. So it will behave like a bar magnet, and you're going to induce a current inside here. If they are not moving, nothing happens. Likewise, and that was done by Faraday himself. If you open the circuit, the magnetic field will collapse. Okay, it's not going to collapse instantaneously, it will collapse little by little. So the number of field lines will decrease. Okay? Everyone is very talkative today. What's happening? Is there something happening outside? I saw that they had food outside. You see, when you turn on You turn on the power supply, the magnetic field is going to increase, is going to expand, but it takes time. And if you have a solenoid with a magnetic field again, you turn it off, the circuit, the magnetic field is collapsing, so you get less lines, but it takes time. Right? No, it's good to be talkative, okay? The friends that you make in college, you're gonna keep it, you can keep them forever. Everything is connection, connection, connection. So yeah, talk to each other is great. Okay? So what matters is the change. So you go in, you increase the number of lines poking through this area, you move away, you decrease the number of feed lines poking through this area. Is that clear? Okay? And you're going to induce a current, induce a EMF. So what's the equation? The EMF induced will be equals to the number of loop times the change in magnetic field flux. And the magnetic flux is the number of lines poking through this area. So that will be the equation that you want to use, okay? And we did an example here. We're going to try to do this. Do it! Now. Do it, do it, do it, do it, do it. Okay, so the magnetic field is where? In the screen or towards you? In the screen. Okay. And then it's going to change with time. So it's going to be weaker, stronger, weaker, stronger. So that means the lines here poking through this area is going to change with time. So it's like you take a magnet or you take an electromagnet, even better. You take an electromagnet, you go in and then you go out. You go in and then you go out. So the number of lines poking through the area is going to change with time. Okay, so you can do it. So let's look at this area here. Shh. So I am attaching an area. It's imaginary. Okay, it's like a soap film. So that will be your area here. And that will be your EMF. So the EMF equals the number of loops, okay, inside the conductor, how many times you go around, times the change in flux. And I told you the magnetic flux will be the area times the magnetic field. Magnetic field has to be perpendicular to it, okay? Otherwise, you have to use a cosine, but we don't have to worry about it. It's perpendicular to the area. Okay, are you doing it instead of talking over there? So it's going to be B2. Okay, it's a change, so final minus initial divided by the time elapsed. And what is changing? We want to know the rate at which the magnetic field is changing and the area is not changing. Do you agree? So the EMF will be equals to, so the number of loop, B is changing, the area is not changing. So you can do it this way. I can factor out the area, which is not changing, so number of loop times the area. And here I have B2 minus B1 over delta T. And what's B2 minus B1? How we call that? Final minus initial, it's a delta. Very good, it's a rate. Okay, final minus initial, it's a rate. And over time, it's a rate. Okay, a delta is a rate, and you divide by the time, it's a rate of change. It's a change, so delta is the change. Final minus initial. Okay, so now you can do it. Final minus initial is a rate. And if you divide that by the time, it's a rate of change. When we say, it's very important for biology, you know, how many rabbits, you know, the change is the number of rabbits. It's a change, right? So how many rabbits change per unit day or something like that, or every day? So the number of loop is 1 in that case. The EMF is 3. The area, it's the area of a circle, that's going to be pi r square. And you want to solve for delta B over delta T. Okay, so every second, what's the change in the number of magnetic lines, magnetic field lines? So pi r square, so the area is pi r square. Are you doing it?
Oh, it's centimeters though.
Oh, you write. Oh, is here. You write it's 0.1. Okay, because it's a diameter. Oh, it's tricky. You see, R is 10 centimeter because the diameter is 20. So it should be 0.1 square. Do you agree, everyone? Are you doing it? Don't space out. So EMF will be equals to number of loop 1 times the area pi times 0.1 square times the rate. And the EMF, it's given, it's 3. Because you want to induce 3 volt, so you can turn on your light bulb. The light bulb is 3 volt. So it's going to be 3 divided by pi 0.1 square. So what do you get? 95.5 Tesla per second. Okay? So it's a rate, okay? Each time you divide by the time, you get a rate. It's like a speed. How fast the magnetic field is changing. So when you divide by the time, it's like a rate. Everyone? Any question? Do you all agree? Okay. So next one is a little bit more challenging. Oh, they have the solution here. Look at that. So right away, they factor out the area. So what you are left with is the rate of change of the magnetic field. And you want to be, you want the EMF to be 3 volt. Bless you. Okay, so this one is a bit challenging. I'm going to start with number 2. Okay, I'm going to start with number 2. So this is not for test 3, but this is for the final. So if you pay attention, you won't have to worry so much about the final. Okay, so a conducting coil with a radius 2.5. So it means a coil, it's something round like this. Okay, maybe it's attached here to a voltmeter, so it's a coil. And you can even draw the area, which is imaginary. Okay, so you have this area. Okay, so radius is 2.5. Okay, so try to do it without me. So that will be the radius, 0.025. So right away you want to convert to meters. Okay, so you catch all the physical quantity, so that will be the number of turns. Okay, so it's perpendicular to magnetic field that becomes stronger. So it means that you have a magnetic field here poking through, and it says it's perpendicular. So it's poking through. So that's before, and after. So I'm gonna draw. So don't wait for me, okay? I'm taking my time. Do it. More you do, less you have to worry for the final. Okay, so now I'm taking the same loop. And now the magnetic field becomes stronger. So it means the number of lines, it's going to increase. You're going to have more field lines. So that will be B2. Okay, I'm translating everything. And here you have a rate. You see, Tesla. So what does that mean? The top here, it means the change in the magnetic field. The bottom should be the time. So that's the meaning of a rate. Okay, it's a change per unit time, which is 1.8 times 10 to the negative 3 Tesla for 1 second. Okay, so it's going to increase at this rate. Like if you say I make $20 per hour, that's a rate. Same thing here, it's a rate. Okay, find the magnitude of the magnetic force. Electromagnetic force means EMF induced in the coil. Give the answer in millivolt. You see, you read, and as you read, you identify the physical quantity and you draw. You can apply the same methodology for any science class. So you can find the area, which is pi r square, so 0.025 square. So that will be your area. Okay, and what's the equation? EMF equals the number of loop, then delta, and then you have B times the area. So I'm going to do it this way. You can do it the other way. That's the equation. And the area is constant, so I can factor out. So EMF equals the number of loop times the area times delta B over delta T. Now, if you are confused here, you can say N B2A2, so after minus before, divided by the time. So you can factor out this area because it's going to be the same. So it's going to be NA delta B over delta T. Right? Someone marked present and then is not here anymore. So anyway, okay, so let's compute. So the EMF equals the number of loops, so it's going to be 150 times the area, so pi times 0.025 square times this here, 1.8 times 10 to the negative 3. So the EMF equals, so number of turns times the area times the rate of change, right? So it's going to be very good. And so now we have to turn that into millivolts. Okay, so one millivolt is 10 to the negative 3 volt. So it's going to be what? No, you divide. Because you want to know how many of that goes into here. Oh, you cross multiply, you divide, right? Yes, so 5 times 10 to the negative 4, enter. How many millivolt goes into? So I divide by 10 to the negative 3. It's going to be 0.5. 0.53 millivolt. So you convert, right? 1 millivolt is milli means 10 to the negative 3. Okay? So in millivolt, you cross multiply, divide. Okay? Is that clear? Everyone is good? Okay, so I'm going to go back to 1, but first, this one is also easy and easier. So let's try to do 3. Okay, so talk to each other and try to do 3. Can you see here or it's not clear? Yeah. Oh. Okay, so this is constant. Plus you, it's rectangular. So that will be the area. So that will be area 1, then it goes area 2. And that will be delta T. Okay, take your time to do it, okay? I'm going to try to draw something. No, we have to factor out. So I'm actually 8 minus A1. So 156 times 10 to the negative 3 minus 3. So the magnetic field does not change. Okay, so you have a magnetic field here poking through. Let's say I'm going to make three lines. And what they do is that they decrease the area. So now it's a smaller area. So the area is smaller, but the number of feed lines is the same, except it's missing, right? It doesn't poke through. So maybe you're going to catch only a few of them. So you have less lines poking through. But it's the same magnetic field. So it's like you have a net to catch shrimps, and you decrease the size of your net. So of course you're going to catch less whatever you are catching. So EMF. So the EMF equals number of loop. So B after A after minus B before A before over the time elapsed. So in that case, the B stays the same, okay? So EMF equals number of loops, B stays the same, the area is changing. So you can factor out B. Okay, I did all the steps. So even if you don't like algebra, it should be fine. So this is 1. This is 0.5. And here you have after minus before. Is it normal to get a negative number? If you have a negative number, yeah, it's normal. So for the EMF, you don't worry about the sign. Okay, we need to get to Lenz's law to understand the meaning of the sign. The sign, like it's gonna tell you which way the current is gonna flow. But we'll get to that. So don't worry. Let's just do the absolute value. Okay, so EMF equals number of loop is 1 times magnetic field is 0.5. The change in area will be 3 times minus 1.6, and you have a negative 3 here. And the time elapsed is 1.6. So what you get? So 1 times 0.5, and then you subtract the area after minus area before, and in absolute value, so I don't care about the negative sign. And what do you get? 4.3 times 10 to the negative 4, you sure? Okay, volt. So that will be 0.43 millivolt. Huh? So to get millivolt, you divide by 10 to the negative 3. Oh, because when you have, it's a good question, when you have a voltmeter and you are measuring voltage, if you leave it in volt, you don't have enough decimal after the point. So you move it to millivolt and then you have more decimal points. Any question? Okay, good, good. It's not easy, okay? That part will be the hardest part of this unit. Number let's do number 4. Number 4. Round. So it's round. That will be number of turns. It's connected in series. Okay, so it means you have a coil. Okay, and this is connected to a resistor, and you are measuring the current here. So you see it's like a series. It's a circuit in series, but you have a coil here. And this is the resistance R. Okay, R equals 17 amp. Not amp, ohms. That's the current flowing through the resistor. So you have current flowing through the resistor, and there's going to be 6 amp. So you're gonna induce a current flowing, and then I don't know if okay. So that's gonna be your area. Do it. Don't wait for me, okay? So the area. We don't know the area. So the number of feed lines will change with time. Okay, so it's gonna be 3 Tesla per second. So it means the number of feed lines poking through is gonna change. So it's gonna increase, decrease, increase, decrease. Okay, I take my time. Don't stare. Do it. Okay, good. You have to use Ohm's law. Just use Ohm's law. Ohm's. So the area does not change. So it's just the number of line that is changing. So we have to divide that value by pi to the square to that part. So we got all that value by pi. So yeah. It's something like a it's fine. Yeah. Oh, it's okay. No. It's okay. So the number of lines poking through is increasing. So there is a current induced. And how can we find the EMF? Very good, Ri. Okay, so we use Ohm's law. Because the number of field lines poking through is increasing with time, you're going to induce a current. The current induced is going to flow through the resistor, okay, I, here. So you can find the EMF this way. So EMF equals 70 times 6. So 102 volt. Is that 102? Yeah. Well, it's a big EMF. The radius. Okay, so the EMF equals the number of turns times the area does not change. So the only thing that changed is the magnetic field. So delta B over delta T. Okay? So 102 equals the number of turns 180 times the area. We're going to find the area first. And then we'll figure out the radius times 3. So the area is going to be 102 divide by 180 divide by 3. 0.19 meter square. Did you all get that? That will be equals to pi r square. Guys, do it. If you do it, yeah, time goes faster. I don't hear you. Who is talking? First of all, I don't see. Okay, what's your name? Jackie? Yes. Okay, so Jackie says 0.0. 0.245. What? 245. Okay. Did you all get that? So you isolate r square and you take the square root. Okay, so the answer will be 24.5 centimeters. So if it's a multiple answers question, the answer will be in centimeters. Okay, no, but that's correct, of course, right? Okay. Check. So let's go back. Number 1 is a little bit challenging. Number 1 is a little bit challenging. Do you remember from if something is moving along the x-axis? Okay, do you remember from last semester? If something is moving along the x-axis here, x-axis, that will be the speed is the displacement delta x over delta t. That will be the x component of the velocity. Do you remember that? Okay. Do you agree that if you have a rectangle, that will be the width, that will be the length? So the area is width times length. Do you agree? Okay. So this one is a little bit challenging. So you have this is the magnetic field. Does it go in the screen or toward you? In the screen. Okay. So what's happening here? Okay, so here you have a magnetic field going into the screen. And here you have a loop, so it's a closed loop, okay? It's a conductor, and it's moving along the x-axis. So before it was here, outside the magnetic field. Here it's going to enter the magnetic field. Here it's inside, and here it's leaving. So it's moving in this direction, right? Do they have numbers to give us? Okay, just want there is no number. I think they just want the algebraic equation. So anyway, do you see it's moving at a speed v? Do you agree? So let me ask you something. Are you going to induce anything here? Do you have a change in the number of field lines poking through? Here. Is there any field lines poking through? No. Now, here, yes, you have field lines poking through, right? It's going into the screen. So as it's going into this area, the number of field lines are going to increase. Do you agree? Okay, so imagine you have field lines coming from the desk to the floor, and you have your loop. Here, nothing happens. And as it's going to enter the magnetic field region, here, the number of lines is going to increase. So it's moving. So the number of lines is going to increase. What's happening here? Are you changing the number of lines? Is it changing from here to there? No, you do have feed lines, but they are not changing, right? As you leave, what's going to happen? The number of feed lines will decrease. And then here is still moving. Do you have a change in the feed lines? No, because there is no feed lines. Okay? So you only have a change when you are entering the region. Okay? Do you agree? So if I write down the EMF, it's going to be the number of loop. So in that case, it's going to be 1. And then it's going to be the change in the number of field lines poking through per time. So what is changing in that case? Something has to change. So is the magnetic field changing? No. Is the area changing? The area is changing. This area is not changing, but the area, we want the area poked through by the magnetic field. So only this area is changing, right?
Okay, so when where the actual lines are poking through, so like half of the rectangle doesn't have any.
Exactly. So that we call that x here, right? So it's going to be n. I'm going to just follow the equation. N. So what is not changing? Magnetic field. And the area is going to change. So what's going to be the area? The area will be width times length. But the width here, that will be only the area exactly. That's going to be the x times the length, which is L. So the change in area will be equals to L delta x. So delta A over delta time, the delta t will be L delta x over delta t. And delta x over delta t, it's going to be the speed. So it's a little bit challenging. So in this example, EMF will be equals to the number of loops, the magnetic field, the length, and then here it's going to be delta x over delta t. EMF will be equals to NBLV. So what's happening here? It's because it's moving, okay, because it's going into this region here where you have a magnetic field. You're going to induce a EMF. So mechanical energy will be turned into electrical energy. So this is called the motional EMF. Okay, so it's a little bit challenging, but sometimes it's okay. So that means in that equation, the area that you want is the area poked, that is poked through by the magnetic field. Okay, so it's a little bit challenging. Let's see at the end if you have the equation here. It's called motional EMF. So the EMF will be equals to, can we make it larger? You have the equation here. So go back here. Okay, so don't worry about this one. Oh wait, you do have numbers. Hey, you do have numbers. I didn't see them. Okay, so we can do the computation. Okay, I didn't see that. So what did we get? EMF equals the number of loop times the magnetic field times the speed. Did I forget something? Oh, times the length. That length here. Okay, so now you can compute. See, they give you here, this is T, M, I. So plug in it. So EMF, number of loop is 1, times the magnetic field is 2, times the speed is 2 centimeter per second. So that will be 0.02 times the length is 0.1. So what you get? Hmm? Volt. 1, 2, 3. So 4 millivolt. So that means if you have a magnet in your hand, a bar magnet, and you have a closed loop, okay, and you move the closed loop just on top of your magnet, you're going to induce current. You're going to have current flowing inside through the loop. Okay, and what else do they want? The induced current. So the induced current will be, you use Ohm's law, the EMF divided by R. So it's going to be 0.004 divided by 2, which is 0.002 amps. 1, 2, 3, or 2 milliamps. So this one, did I forget something? No? So this one is a little bit challenging. Right? Because you want to take in account only the area only the area the magnetic field is poking through. Okay, so here you see this area here does not have any magnetic field, so you should not take it in account. So the equation is the flux, the number of field lines equals B times the area poked by the magnetic field. Okay. Any question? I will try to find like an app for next time. Okay, so now we move to the real world. How do we produce AC? So here you have the big idea. You have a magnetic field. Can you see that the magnetic field here, okay, from north to south, for example, and here you have a conductor, it's a loop and it's closed. And the field lines are poking through this area, but the number of field lines will change with time. If the loop is parallel to the magnetic field, there won't be any lines poking through. If it's perpendicular, of course, you're going to have lines poking through. So let's see if I have like this, okay? So imagine this is the magnetic field, okay? So here you have a lot of lines poking through. Here you don't have any line. Here you have, again, maximum lines, no lines, maximum lines. By doing so, you're going to induce a AC voltage. And this is how electricity is produced from the outlet. Now, you see it has a rotational speed. Okay, so we're going to speed at, it's going to rotate at a given speed. So the number of cycles per second, it's going to be 60 hertz. So we're going to produce a AC voltage with a frequency of 60 hertz. Is that clear? So I have an app, AC generator. Let's see. So I discovered that you go on Google and you do GIF. Okay, that's the keyword GIF, and you put generator, for example, or GIF whale, because you are in marine biology for some of you, and you will find GIF, right? You will find like a small animation. So that's very cool. So look what I have found. I'm very proud of myself. We didn't have that. Like when I started teaching like long time ago, like 20 years ago, we didn't have that. That's new. You see the magnetic field goes from north to south, okay? And you make it spin. Okay, so maybe you have a turbine, you have to make the turbine spin maybe with water or steam. You get steam if you are burning fossil fuel, and you see the number of lines poking through is changing with time. Now, how fast it's spinning, meaning the frequency, so how many turns per second, that's going to be the frequency of the AC voltage that you are inducing. Isn't that amazing? So when Michael Faraday did that experiment in front of the king and other people as well, the king said, "Okay, that's cute, but what's the point of it? Okay, it's just cute. It's just an experiment." And Michael Faraday said, "One day, my king, you will be able to tax it." And that's exactly what happened. Okay, when you are paying your electric bill, electricity is very cheap. What you are paying is the tax, right? The transportation but otherwise, electricity is very cheap. How cheap it is to make something spin inside the magnetic field. That's not hard. Okay, I have another GIF. uh, oh, is that the same one? Okay, I want this one. Okay, you get the idea? That will be called the rotor. Okay, and you have to make it spin, and you're gonna make AC. And I have another one. I think I downloaded all of them. So this one is nice because you have your load here. Your load could be the household, and you see that the voltage is AC. So the EMF, the voltage induced, is going to be alternating voltage. Isn't that cool? Huh? The genius, Michael Faraday, who didn't go to school. Genius, right? So how do we produce electricity? Okay, so you're gonna have something that will spin here, okay, which is called the rotor, and this is called the stator. So I want to show you. I don't know the movie, what it's called. Video.
All generators use induction to create an output voltage. When the output of a generator is connected to a circuit, the induced voltage causes current to flow through the circuit. There are three requirements for inducing voltage. First, a conductor must be available to carry current. The second requirement is a magnetic field. Third, there must be relative motion between the conductor and the magnetic field. In this illustration, a wire is wrapped around a metal ring. The wire serves as the conductor that carries the current that results from induction. The second requirement, a magnetic field, is created using a magnet. A permanent magnet like this one can be used to induce voltage, but the magnetic field it creates is very small. Electromagnets are used to create controllable magnetic fields that are strong enough to induce large amounts of voltage. This is a basic electromagnet. It consists of a coil of wire wrapped around a metal bar or core. When electric current from a source of direct current flows through the wire, a large concentrated magnetic field is created. The wire may be referred to as the field winding because it helps to create the magnetic field. The third requirement for inducing voltage is relative motion between the magnetic field and the conductor. Here's an illustration that shows how voltage is induced when the electromagnet rotates. This electromagnet has a north pole and a south pole. The magnetic fields at the two poles are opposite in polarity. As the electromagnet rotates, the magnetic fields cross the conductor and induce a voltage. We can say that the north pole induces a positive voltage and the south pole induces a negative voltage. Generator output can be represented as a sine wave that is plotted on a graph. On this graph, the vertical axis represents the strength of the voltage, which can be positive or negative. The horizontal axis represents time. As the electromagnet rotates, the relative positions of the electromagnet and the conductor affect generator output as shown on the graph. When the electromagnet is vertical and the magnetic fields don't cross the conductor.
So you see here, you don't have flux, right? There is no field lines poking through this area. You can imagine there is an area here attached. And then it's going
The
to
voltage
spin,
is zero.
increase the flux.
Now, as the electromagnet rotates through the first quarter of a complete revolution, the output increases to maximum in the positive direction, and then drops to zero again as the magnet reaches a point 180 degrees from its starting position. As rotation continues, the simplified illustration of a generator. The current flows from the winding, each of the three stator windings at different times. Consistent. Equipment that you...
And then it goes more in but you get the idea, right? I have just one picture to show you. Yeah. So it's always the same things. One is moving, which is called the rotor. Okay. So the rotor, you have a coil, so that will be your conductor. And this is connected to the high tension lines that you see outside. and that will be 100,000. So you're going to have a small voltage produced, then you step it up to 100,000 volts, okay, through the high tension line. When it gets to your house, close to your house, it's going to be stepped down to a few 10,000 volt and 120 volt. And this is called the stator here. So this one is not moving, and this one will have a magnetic field because you can connect it to a DC power supply. Okay, we'll I'm gonna it's gonna be more math, so I leave that for next week. Can we finish 5 minutes early? Everyone agrees? Okay.